Right, as a first revision problem, let's look at the task of finding the open box of greatest volume that you can construct from an A by B sheet of, say, cardboard, like this, by cutting out the corners and folding up the sides. So let's suppose we cut out the corners like this, and then fold up those sides. What's the volume? And then how do we choose this to maximise the volume? So let's call the amount that we cut out X, which we don't know yet, in each direction. Then the volume will be the base area, which is A minus 2x from there to there, times this distance, which is B minus 2x, and then the volume is that times the height, which will be x. So the thing we want to maximise is A minus 2x, B minus 2x times x. And we'll do this with standard calculus, which you recall involves finding the zeros of the derivative of this and then using the second derivative to see whether it's a maximum or a minimum. Alright, so let's do this by expanding out this formula. Cubic in x. There is a term linear in x, which is a times b times x. And there's two terms in x squared. There's minus 2x times b times x. And there's also a times minus 2x times x. So put those together, and that's minus 2a plus b times x squared. And then there's an x cubed term, which is minus 2x times minus 2x times x. That's plus 4x cubed. Alright. To find maxima or minima, we set the derivative to 0. So what is the derivative? Okay, polynomial, it's straightforward. Right. AB, derivative of x squared is minus 4a plus bx. Derivative of 4x cubed is 12x squared. Right, our aim is when that is 0. And then we'll check on maximum and minimum with the double derivative, the second derivative, which involves differentiating this, and that is just 4ab and plus 24x. Okay, now let's solve this equation equal to 0. It's a quadratic in x, so we know a well-known formula for its solution. The old, okay, namely, v dash x is 0 when x is minus this coefficient, so that's 4a plus b, plus or minus the square root of this coefficient squared, so that's 16a plus b all squared, minus 4 of 12 times ab, so that's minus 48ab. And all that is divided by 2 times that coefficient, 24. Okay, we can simplify this. There's a factor of 4 that we can cancel. 4 and 4's into 24 goes 6. But we also need to cancel out a 4 from this square root. And 4 outside the square root becomes a 16 inside the square root. So that cancels with that one. And 48 divided by 16 is 3. So our result is x is equal to 1/6 a plus b plus or minus the square root of a squared plus 2ab plus b squared minus 3ab. We've got 2ab minus 3ab is minus ab. So let me just rub that out and put a minus in it. So there's two cases. One's a minimum and one's a maximum. Which is which? We'll get by looking at the second derivative. second derivative is minus 4a plus b plus 24 times x, which is this expression. So 24 divided by 6 into a plus b plus or minus the square root, which I won't write out in full. Now, 24 divided by 6 is 4. And we've got minus 4a plus b and plus 4a plus b, so that cancels with that, leaving us with just plus or minus 4 times the square root, which is a squared minus ab plus b squared. I'll put it in here. Now, out of the two of these possibilities, this is less than 0 and hence a maximum for the minus case. And the minus case is what we want for a maximum, because at a maximum the function curves downwards. It's got a negative second derivative. Okay, so yeah, that's the x. So for example, even more specifically, what about the case a is equal to b? So this is a square bit of cardboard. So in this case, the optimal x is 1/6 into a plus b, which turns into a plus a, plus or minus the square root of a squared minus ab, which is another a squared, plus b squared, which is another a squared. And you can see this all simplifies nicely. That's the square root of a, so we either get a plus a, so that's 1/6 of 3a, or we get 1/6 of a plus a minus a, that's 1/6a. So maximum or minimum of x is a half a or 1/6 a. Now, out of the two of these, the maximum, the greatest volume occurs in the minus case, and that's this one. Right, that gives the maximum volume. And that's the solution for our problem about what to cut out.